Section 7.3 is hyperbolic functions. I'm not going to do a whole lot with hyperbolic functions. I'm actually not going to do anything with hyperbolic functions other than have you work some homework problems. I just want to expose you guys to them and tell you what they are because you may see them in future classes, especially physics. So there are 6 basic hyperbolic functions. There's the hyperbolic sine. The graph of the hyperbolic sine looks like this, and it's written similar to sine, but it's sinh. That's how you pronounce this. It's sinh x. It's actually equal to an exponential function, e to the x minus e to the negative x divided by 2. So if you're working with a hyperbolic sine function, you can either work with the hyperbolic sine, or if necessary, go back to the exponential function that it's equal to. There's a cosh, the hyperbolic cosine. It looks like this. And this is what the hyperbolic cosine is equal to. It's e to the x plus e to the negative x divided by 2. A lot of the trig identities that you learned for trig functions are going to carry over exactly the same, and some of them are going to be similar. So for example, hyperbolic tangent or tanh is equal to sinh divided by cosh. Well, that makes sense because tangent's equal to sine over cosine. So that holds true. And if we were to set the exponential functions for the sinh and the cosh equal to this, we would end up with e to the x minus e to the negative x divided by e to the x plus e to the negative x. So that property holds. Hyperbolic secant is 1 over hyperbolic cosine. Hyperbolic cosecant is 1 over hyperbolic sine. Those reciprocal identities for the basic trig functions are going to carry over into the hyperbolic functions, the hyperbolic trig functions. So those identities are easy to remember because they're similar. But some of them are not the same. We have a Pythagorean identity in trig that says sine squared plus cosine squared is equal to 1. Well, when you're dealing with hyperbolic functions, cosh squared minus sinh squared is what's equal to 1. That's different. We have a double angle formula for sine that says sine 2x is equal to 2 sine x cosine x. That mirrors this identity for the hyperbolic trig functions. Sinh 2x is equal to 2 sinh x cosh x. So you've got to look through these identities basically and see what looks the same and what looks different. Or for the sake of homework, just keep this page of your notes open so that you can work with the identities as they're given. We're able to take derivatives of hyperbolic trig functions just like we're able to take derivatives of trig functions. The derivative of sine is cosine, while the derivative of sinh is cosh. The derivative of cosine is negative sine, but the derivative of cosh is positive sine. That's different, whereas this one was the same. The derivative of tangent is secant squared, while the derivative of tanh is sec squared, which is the hyperbolic secant function. That's the same. This one's the same. The derivative of hyperbolic cotangent is equal to negative hyperbolic cosecant squared. That's the same as it is because in regular trig functions, because the derivative of cotangent is negative cosecant squared. So some of these are the same, some are different for the derivatives from what we learned for the basic trig functions. Same thing with the integrals. Some are the same, some are different. When you graph a hyperbolic trig function with the inverse of the hyperbolic trig function, you're going to once again see symmetry about the line y equals x, because anytime we graph a function with its inverse, it will always have symmetry about the line y equals x. We learned that in college algebra, I believe, or pre-cal. And then we have the properties of the inverse hyperbolic trig functions. Just like with regular trig functions, the way you get an inverse function from the function is you switch x and y. To get an inverse from a function, you just switch x and y and solve for y. So the graphs of the inverse hyperbolic tangent, cotangent, and cosecant functions of x are given above. And here we have identities for inverse hyperbolic functions. And then also integrals and derivatives for inverse hyperbolic functions. I'm not going to do a whole lot with those. The types of questions I'm going to ask you on the homework is just going to deal with some of the basic identities for the hyperbolic trig functions. So in example 1, we're told that if hyperbolic sine of x is equal to 8/15, we want to find the remaining 5 hyperbolic trig functions. How we can go about doing this is by using one of the identities. So for example, we have a Pythagorean identity. The hyperbolic cosine squared x minus the hyperbolic sine squared x is equal to 1. So what we're going to do is we want to figure out what cosh is. So we're going to plug in 8/15 for the hyperbolic sine and then solve for cosh. So that's going to give us hyperbolic cosine squared x minus 8/15 squared is equal to 1. Well, what is 8/15 squared? 8 squared is 64, divided by 15 squared is 225. So then we would add 64 over 225 to both sides of this equation, and that's going to give us the hyperbolic cosine squared is going to be equal to 289 over 225. How do I get the square off of this hyperbolic cosine? Take the square root. What you do to one side, you have to do to the other. When I do that, that means that the hyperbolic cosine is going to be equal to 17 over 15, because the square root of 289 is 17 and the square root of 225 is 15. So now we know numbers for sinh and cosh. How do we get tanh if we know sinh and cosh? Well, we had that ratio identity that said that the hyperbolic tangent is equal to the hyperbolic sine divided by the hyperbolic cosine. So that's going to be 8/15 divided by 17/15. And when you divide a fraction by a fraction, you flip the one on bottom and multiply by the one on top, and that's going to give us 8/17. So the next one I want to get is cotangent. The hyperbolic cotangent is just the reciprocal of the hyperbolic tangent. The hyperbolic cotangent would be equal to the hyperbolic cosine over the hyperbolic sine, and that's going to be equal to the reciprocal of this is 17 over 8. What about the hyperbolic secant function? That's going to be equal to what? The reciprocal of the hyperbolic cosine, because secant is the reciprocal of cosine. Well, when I look at the reciprocal of cosine, that's just going to give us 15 over 17. And then the last one that we need is the hyperbolic cosecant. So that means the hyperbolic cosecant is going to be 1 over the hyperbolic sine, and that's going to be 15 over 8. And this is our final answer. We've got all the remaining 5 hyperbolic trig functions. The ratio and reciprocal identities work the same for the hyperbolic trig functions as they do for the regular trig functions, sine, cosine, tangent, and so forth. Example 2, we're asked to find the derivative of y with respect to x for y equals 8 hyperbolic sine x over 5. Just so we don't have to go back and look at it, I'm going to write down what the derivative is for hyperbolic sine. The derivative with respect to x of the hyperbolic sine of x is equal to the hyperbolic cosine of x. Now all of the rules of calculus still apply for these hyperbolic functions. We still have the product rule, the quotient rule, the power rule, chain rule, things like that. That's what's going to come into play whenever we take the derivative of this function, y equals 8 hyperbolic sine x over 5. That x over 5 I could write as 1/5 x, because that would make taking the derivative easier. So when I take the derivative of y, I get y prime. You have a constant times your function. When you take the derivative, that constant stays there. The derivative of hyperbolic sine will be the hyperbolic cosine. Leave the angle alone. Then you have to multiply by the derivative of the angle, and that's from your chain rule. So that means that the derivative is going to be equal to 8/5 hyperbolic cosine x over 5. That's not too bad, is it? I don't have a whole lot of homework questions asked about these, and I tried to take the basic ones just to get you comfortable with working with these hyperbolic trig functions. In example 3, we're asked to determine the derivative of y with respect to v for y equals the natural log of the hyperbolic cosine 2v minus 1/2 the square of the hyperbolic tangent of 2v. In order to do this, you need to recall that the derivative of cosh is sinh. It's the hyperbolic sine. It's not negative sinh. The derivative of the tanh is sech squared. So for this problem, we've got y equals the natural log of the hyperbolic cosine of 2v, where 2v is the angle, minus 1/2. And now instead of writing this as tanh squared like that, what I'm going to do is rewrite this without the function notation, more using the properties of exponents. So this means that this is equal to tanh 2v quantity squared. I think it's going to be easier to see how to use the chain rule if you rewrite this square as the quantity of tangent squared. Now we're ready to take the derivative. Derivative of a natural log is going to be the derivative of the argument over the argument minus 1/2, and then I've got to use the chain rule. So that means that the 2 is going to come down front times the inside of the parentheses. Subtract 1 from 2 and you get 1, so that's raised to the first power. Now times the derivative of what's on the inside. The derivative of tanh is sech squared 2v. And then you have to multiply by the derivative of the angle, and the derivative of that angle there would be 2. So cleaning this up, what's the derivative of cosh 2v? Well, the derivative of cosh is sinh 2v times the derivative of the angle over cosh 2v minus, and this 2 will cancel out, but I still have a 2 out at the end, so I'm going to move that 2 up front, and that's going to give us tanh 2v times sech squared 2v. I can clean this up further, can't I? This 2 that's in front, I could bring down. And what's sinh over cosh? Sine over cosine is tangent, so this would be the hyperbolic tangent of 2v minus 2 tanh 2v sech squared 2v. And that would be our final answer. This problem had the chain rule in it and multiple iterations of the chain rule even. We could factor, you know what, let's go further because we have a common factor here. What happens if I factor out a 2 tanh 2v? Let's just keep going. I would accept this answer if I were giving this problem on a test, but when you check your answer in the back of the book, I think they went a little further. So if I factored out my common factor, what I'm left with is 1 from this first term minus the hyperbolic secant squared 2v. Let's go look at our identities right quick. I believe this is a Pythagorean identity. I think this one would be one of the Pythagorean identities. So if we scroll up, look at this identity right here. I have 1 minus sech squared. That's equal to tanh squared, isn't it? So what I'm going to do is I'm going to replace that 1 minus sech squared with tanh squared in our problem. So when I replace this with tanh squared 2v, I end up with tanh squared times tanh is tanh cubed. So this ends up being 2 hyperbolic tangent cubed 2v. And that would be our final answer. I would be okay with this, but your book might have this as the answer in the back of the book. As long as your answer can be algebraically manipulated into the answer that's in the back of the book, know that it would be okay for me on a test where you have to write out your work. Let's try an integral problem. Here we're asked to evaluate the integral of hyperbolic sine 5x. I would want to do a u substitution with this one. What would I let u be equal to? 5x. So what is du equal to? 5 dx. I don't have the 5 there, so I've got 1/5 du is equal to dx. So in place of this dx, I'm going to plug in a 1/5 du. That means that I can rewrite this problem as 1/5 the integral of hyperbolic sine u du. And when we integrate hyperbolic sine, that's going to give us hyperbolic cosine. Don't forget the plus c. But I don't want to leave this as my final answer. Why not? Because this answer has a u in it. My original problem had an x in it, so I've got to put the x back in, which means that this is going to be 1/5 hyperbolic cosine 5x plus c. And that's our final answer. One thing I want to caution you about is if you're working with the hyperbolic trig functions, don't let them mess you up with the rules that you've already got memorized for the integrals of regular trig functions, because the integral and derivative of the hyperbolic sine are different. Well, at least the integral is different for the hyperbolic sine, because the integral of sine would be negative cosine, but the integral of hyperbolic sine is positive hyperbolic cosine. All right, last problem. Here we're asked to evaluate the integral. negative natural log 6 to negative natural log 3 of 2e to the theta hyperbolic sine theta d theta. In order to do this, I do not want to work with the hyperbolic sine written like this. If you will recall, I said that the hyperbolic sine is equal to e to the x minus e to the negative x divided by 2. This is what I want to replace this hyperbolic trig function with. And that will allow me to rewrite this problem as the integral from negative ln 6 to negative ln 3 of 2e to the theta times e to the theta minus e to the negative theta over 2 d theta. So these 2's will cancel out. And then I can distribute this e to the theta across. And when I do that, I'm going to get the integral from negative natural log 6 to negative natural log 3 of e to the theta times e to the theta is e to the what? When you multiply with a common base, what do you do to the exponents? And theta plus theta is 2 theta. Minus e to the theta times e to the negative theta. You're multiplying with a common base, add the exponent. So theta minus theta is 0, and e to the 0 is 1. So now we integrate this. What do we get when we integrate e to the 2 theta? We get 1/2 e to the 2 theta. And what do we get when we integrate 1? Just theta. And then we're going to evaluate this from negative natural log 6 to negative natural log 3. So using the fundamental theorem of calculus, now we're going to plug in our upper bound minus and then plug in your lower bound. So when I plug in my upper bound, I get 1/2 e to the 2 times negative natural log 3 minus negative natural log 3 minus, and now when I plug in my lower bound, I get 1/2 e to the 2 times negative natural log 6 minus negative natural log 6. And now I need to clean this up. Do you remember the power rule for logs? It says that if you have a constant times the natural log of a variable, that's equal to the natural log of the variable raised to that constant power. I'm going to use that to rewrite this. So this becomes 1/2 e to the natural log 3 raised to the negative 2. Minus a negative becomes plus natural log 3. Minus 1/2 e raised to the natural log 6 raised to the negative 2 plus natural log 6. The ln's and the e's are going to cancel each other out. So that means I'm going to have 1/2 times 3 to the negative 2. But what's 3 to the negative 2? It's 1 over 3 squared, and 3 squared is 9. Then over here, the ln's and the e's are going to cancel each other out, and I get 1/2 times 6 to the negative 2. But 6 to the negative 2 is 1 over 36. I then need to come through and simplify this and distribute that negative, and when I do that, that's going to give me 1 over 18 plus natural log 3 minus 1 over 72 minus natural log 6. Now I have like terms I can combine. I can combine the 1 over 18 and the 1 over 72 and the natural log 3 and the natural log 6. Before I do that, I'm going to rewrite this as 1 over 18 we can write as 4 over 72 minus 1 over 72, and then plus the natural log of 3 minus the natural log of 6. We can combine these logs using the quotient rule. Do y'all remember the quotient rule? So this is going to give us 4 minus 1 is 3 over 72 plus the natural log of 3 divided by 6. So 3 goes into 72 24 times, so this becomes 1 over 24 plus the natural log of 1/2. You can write your answer like this, or you may sometimes see it written like this. Rewrite that 2 as a 1/2 as a 2 raised to the negative 1, and that becomes minus the natural log of 2. So I would accept either one of these as your final answer. I'm telling you that not necessarily for this problem, but whenever you're simplifying future problems. The reason I wanted to show you how to rewrite the natural log of 1/2 as negative natural log 2 is because sometimes when you're checking your answers in the back of the book, you may see it written one way or the other, and you need to know how to switch back and forth. How I was doing that was by the fact that the natural log of 1/2 I could rewrite as the natural log of 2 raised to the negative 1. Then using this power rule up here, I could bring that negative 1 down front and just have the natural log 2. That's using that power rule. Okay, and this wraps up section 7.3.